In this video, we'll do some work on velocity time graphs. Another way you can refer to them is as a speed time graph. So velocity or speed, as far as I know, it's pretty much the same thing. Some physicists might disagree with you if you say that, but me, I'm a mathematician, so I'm not really that bothered with the terminology. So, velocity time graphs. So, first of all, on my axis here, I'm going to have time, because everything is going to happen in terms of time. This is just the basics to get us going. And then we're going to have our velocity or our speed on the y-axis there. Now, it's important that we understand what's happening in this graph, and you should probably check my other video on distance time graph to just compare the two. But here, what we have going on here is acceleration. So imagine you pull up at a traffic light, you're at a dead stop, and then the light goes green and you start driving. As you notice, this line is going up, thereby covering time and speed. And speed is obviously changing as it's going up, because the speed is not staying the same. By the time the time moves on a bit, it's faster and then faster still, and then it gets to this point. So this is acceleration. Acceleration is the rate of change of speed. So I can say that acceleration is speed over time. Okay, so that's my acceleration there. It'll be the same for deceleration, which is what this line is here, because you're probably driving along, you get to another red light, you start slowing down. So this is going to be my deceleration, because speed is reducing and coming to naught here. All right, and then up here, what we have, the speed isn't changing. It's not going up or down. It's just constant. So yes, that is called constant speed. So we'll just write that down as constant speed, okay, or constant velocity. All right, so while I'm here, I might as well do a few things to define what we're going to do. So for example, obviously, just that I've mentioned that acceleration and deceleration is calculated by the rate of change of speed over time. So basically what you're actually doing, if I do speed, how far something has traveled, so if this is speed here, speed, how far something has traveled, and I divide it by time, can you see that what I'm actually doing is finding the gradient of this line, rise over run? Can you see that? And it'll be the same thing here, rise over run. So basically, in order to calculate acceleration from a speed time graph, you just find a gradient of the area of, well, the space at which you're finding your acceleration for. And then last of all, in order to find the distance traveled, so distance, what you need to do is find the area on the graph. So basically, if I want to find the total distance traveled here on this graph, this is in the shape of a trapezium. I just find the area of this trapezium, and that's going to be the distance traveled. Be very careful when you're solving questions like these, because they might ask you for the area at a specific region. So it might be just the distance traveled while the car is accelerating. So in that case, you're just finding the area of this triangle. Or they might say, what's the area while the car was driving at constant speed? Then you're just finding that rectangle. Or they might say the area, the distance traveled in the whole journey from that traffic light to that traffic light. Then in that case, you find the area of the whole thing. All right, all of this is just talk until we do a question. So let's do some questions. All right, so let's put some context to this question. This question shows the velocity of a train traveling between two stations. So we've got the first station here, and this is the next station here. So it looks like, so all the time here is in hours. It started off here at 0. It goes up, and it took half an hour to accelerate. So because that's going to be 1 hour here, so this is going to be half an hour. Then we've got 3 hours there, and this is going to be 3.5 hours. So this is, you know, pretty long journey on this train. And as it being a train, half an hour to accelerate is not really unrealistic. So we've got half an hour acceleration. It then drives at constant speed for what is 1, 2, 3 hours. Sorry, 1.5, 2.5 hours there, do beg your pardon. And then it decelerates in half an hour. Okay, so, well, let's see where we're at. Now, the questions that we need to answer: what's the maximum velocity of the train during the journey? That's really easy, because the maximum velocity would be the very, very top of the graph. So it looks like it's going to be, this is velocity in kilometers per hour, so it's about 45 kilometers per hour. So we're going to say that max velocity is 45 kilometers per hour. So that's that, because this is your speed going up here. Then the initial acceleration. Your initial acceleration is your first acceleration, and that's going to be this whole line here, because that's your initial acceleration. Just to put some context in this, a little bit more context, I'll just do a little bit of an aside just here. You can have something accelerating here, probably go on for some constant speed, and then accelerate again to a higher speed, and so on. So you can have an initial acceleration, then another acceleration, your second acceleration, if you want to call it that. But that's basically what that is. All right, cool. So when they say the initial acceleration, they're basically asking you for the acceleration here. Now, as we mentioned in the previous slide, acceleration would be finding the gradient of this line, because it is velocity over time. We've got a velocity for that whole acceleration there of 45 kilometers per hour. It took a time of half an hour, so 0.5 hours there. And so that's going to be equal to 90 kilometers per hour square. Now, let's have a look at why this the units are like this. You've got kilometers divided by hours divided by time in hours again. This is time in hours, and notice I use 0.5 rather than 30, okay? It's time in hours again. Well, we don't divide fractions, we normally multiply them. So this is the same as kilometers per hour times by 1 over hours. You end up multiplying these 2 hours here, so acceleration will normally have a square with it. So kilometers per hour square, like that, or meters per second square if it's, you know, that way, and so on. So be very, very mindful of that. Anyway, let's carry on. The next thing is calculate the deceleration at the end of the journey. You know that the deceleration would be the same as the acceleration, because it took half an hour to decelerate. So it'll be the same as that. The only difference is that it's going to be negative. Okay, so I wouldn't really worry too much about calculating that. Let's move on to find the total distance traveled. So the total distance traveled is the area of your trapezium, which, as we mentioned before, area of that. Now, if you remember your formula for the area of a trapezium, it's a half the sum of the parallel sides times the height, or the distance between the parallel sides. So be very careful with what you put in here as well. So that's a half. Let's have a look at what's happened here. This train traveled for 3.5 hours. So I'm going to say 3.5 hours plus. It was running at constant speed here for what is 2.5 hours there. So we've started on half an hour. That's 1 hour. That's 2 hours at 2.5 hours, and then you need another half an hour to get to 3. So basically it's 2.5 hours running at constant speed. And then it, sorry, I forgot the last bit there now, which is you're timesing by the distance between them, which is 45 kilometers per hour, sorry. So you just times that by 45. All right, so a quick bit of calculations here is going to give us a half of 6 times 45, which is going to be 135 kilometers. Okay, remember it's distance you're finding, so that's going to be in kilometers. And that's it, guys. That's pretty much it. The most we can do is probably have a look at a couple more questions, because the video is now gone past 10 minutes. So a couple more questions, and then, or one more question I would say, and then we're done. All right, so if you stumble on a pretty troublesome question where a graph has not been given to you, then you'll need to draw one. So I've taken the liberty of started labeling my axes here. So you can see why I've gone up to 60 meters per second for my velocity, and my time is in seconds. I should probably put a slash and say that that's time in seconds. I read the question before, so that's why I knew how to draw it, but let's go through the question. So a car accelerates for 8 seconds, causing its velocity to increase from 0 meters per second to 48 meters per second. They're going to ask us to draw the velocity time graph, so we might as well start doing it now. So as you read a bit of information, just try to draw that bit. I don't like this question because they didn't say that it accelerates constant. There was a constant acceleration, because you can end up with curves and things like that as a velocity time graph. It's the same principle, but except you're finding gradients in a different way. But if we got time, I might do one of those questions so that you can see what it looks like. So the car accelerates for 8 seconds, causing its velocity to go from 0 to 48. So this is where my 10 is. So 8 seconds will bring me about there. And then 48. So if this is 50 here, then 48 should be matching with that 8 seconds, somewhere about there. And then all I now need to do is literally draw that acceleration. So that's the acceleration done. It now says that the car travels at a constant velocity, so it's not getting higher or lower. Okay, so it travels at constant velocity of 48 meters per second for 20 seconds. So 20 seconds later will put me on 28 seconds. So I should mark up my 28 seconds. And so bringing that line all the way up, that should be somewhere about there. And I will now draw my constant velocity. Bring that line back a little bit. Perfect. Now, last of all, the question now says the car decelerates for 5 seconds, but it doesn't go all the way back to 0. In that 5 seconds, its final velocity is 23 meters per second. Okay, so let's follow that. 23 meters per second. So that's going to be halfway between here. And 5 seconds later, we'll be on 33 seconds. So let's see if I can find my 33 just there. And then I'll go all the way up to 23 meters per second. Oopsie, just come off the line just a little bit. That's where I really need to be. And I will now just draw my line going down there to represent my deceleration. Okay, perfect. All right, cool. That's fine. So that's pretty much my velocity time graph that shows the car's velocities during this part of the journey. Now they want us to calculate both the acceleration and the deceleration of the car. So as you can pretty much guess, we will need to calculate the gradient of that line and the gradient of this line. So acceleration is velocity over time. So here we go. So our acceleration, velocity of 48. The time it took was 8 seconds. So that's going to be 6 meters per second square. You can write it like that, or you can write it with the minus symbol. All right, so not a particularly fast car, not by today's standards anyway. And then we'll do our deceleration. Now for our deceleration, we've come down from 48 to 23. So that's going to give us 25. So this is going to be 25 is the reduction in distance there. And it's only done that for 5 seconds. So therefore, our deceleration is equal to the speed, 25 divided by 5, which is 5 meters per second square again. The difference is now I didn't do this here. Ideally, this should have been negative, okay, because your speed is decreasing. Deceleration really should be negative. In many cases, it's accepted as positive, but it really should be negative. And then obviously, for the bigger one, distance traveled. So what we'll do for this, we can, I don't know, chop this up anyhow we like, really. So we can go for a triangle here, which I can call A. And then we've got a rectangle here, which I'll call B. And then we have a final triangle here, which I'll call C. Okay, because the car stopped moving at this, well, not stopped moving, it started at its constant speed by this point here, which we can imagine will just carry on going there. So we'll call that C. All right, let's move this up a little bit, and then let's start our work. So for this triangle here, we know that that's going to be a half base times height. So we're looking at a half, the base is 8 and the height is 48, as you can remember, because that's 8 and then we got 48 going up there. And that's going to be equal to pretty much 4 times 48, so that's 192 meters there. Then we've got the area of B, that's a rectangle, so length times width, where we have a length of, well, doesn't really matter, so that's going to be 48 there, so that's 48, and a width of 20, so that's going to be our 20 here, because it's a rectangle. That's going to be 960 meters. And then last of all, for C here, we have another triangle, so we will carry on doing a half base times height on that one. So that's a half, the base is 5, and the height is 25, if you remember well, because we've just calculated it over here. So that's 25, and that is 5 seconds there. And that's going to give us 62.5 meters. So therefore, the distance that this car has traveled is going to be the sum of all of these, 192 plus 960 plus that 62.5, which is going to give us a grand total of 14.5 meters. All right, so that's basically it there, guys. All right, guys, so this is the final question. This video has gone on way longer than I wanted it to go. But anyway, this is just to give you an idea as to how it can look as well. So we've been doing lots of stuff on constant velocity. I mean constant acceleration. So that was a straight line going up here. So now we have a curve, which means this acceleration is not constant, okay? It's changing over time in various ways. You have a suggestion of constant velocity here, but it's still not constant because its acceleration is still increasing. You have a peak velocity and then deceleration there. All right, so let's crack on. So this question shows the velocity of an object over 60 seconds. So you can see it starts here, goes up to 60 seconds. It's been split up into 20-second intervals. So you can see what's going on in this first 20 seconds and the next 20 seconds and then finally that. And then it says estimate the distance traveled during the first 20 seconds of the journey. Now, this is going to be an estimate purely because in order to find the exact exact distance traveled and finding the area on this graph, we really need to integrate. But this is for GCSE purposes, so we're not going to integrate. What we're going to do though is that we're going to make a bunch of little trapeziums and we're going to use that. Okay, it's also going to be an estimate because we're going to be missing bits out. So for example, I can make, let's use a different color, I can make a little triangle here. So we'll find the area of that triangle. And then I can make a little trapezium here and a trapezium there. And finally a trapezium here. So you can pretty much guess that this could get really lengthy. But what I will do is I will shorten this so that it's not that painful. Let's first of all start by dealing with this little triangle here. This triangle goes on for 5 seconds and it looks like it goes to about 8 meters per second there. So therefore the area of this little triangle is going to be a half base times height as usual. So that's a half times 5 times 8, which is going to be 20 meters. Okay, that takes care of that. Now, in order to work out these bits here, what we'll do, let's just check their length first, and then we're going to use the trapezium rule. So I reckon this goes up to 15. This will probably be about 22. And this will probably be about 26 there. All right, cool. So what we're going to use is a trapezium rule with three strips. The trapezium rule merges basically all of the area of the 3 trapeziums here together into one long rule. And it's very easy to remember. The area there for the trapezium rule is going to be a half times the distance between all of the strips. And because I've chosen my strips wisely, the distance between each of them is 5. So therefore it's a half times 5. And then we're going to do the length of the first strip. So basically this first one here plus the last one times 2 times all the bits in the middle. So the first one, which we said, actually, let's just put the numbers in straight away just to save time, all right? So what did we say? Half times 5, that's the width between. The first strip we said would have been 8. The last strip we said would have been about 26. Plus 2 times all the other strips in the middle. And we've only got literally 2 strips in the middle, this one and that one. So 15 and 22. So therefore 15 plus 22. And then I'll quickly calculate that. Yep, and that gives us about 270 meters, okay? Obviously, if we integrate it, we'll probably have more accurate answers, but this is just an estimate because there are obviously spaces between where the trapeziums there, obviously because my pencil is a little bit fat, you're not going to see the spaces, but there are spaces there. All right, now we want the last 20 seconds of the journey. So same sort of scenario we got here for the last 20 seconds of the journey. So what I will do this time, I'm not going to split it up into as many parts because like I said, it is just an estimate. So I might just do, let me see if I can get away with this. Okay, probably not so much. So you know what, let's just get on with it and do exactly what I did before. So what I will do is I will sort out this little triangle here first. And then I will do these 3 trapeziums using the trapezium rule. This time I'm not going to hang about and explain all that to you because time is of the essence. So I'm literally just going to pause the video and just do it. If you want, you can pause the video, see if you can do it before I do it. Okay. All right, so I've decided to bring you in from here. So what you will notice I've done so far is I found a little triangle here, half base times height, so 5 and 5, so it gives us 12.5. And then I've made my little trapeziums. I've put my numbers in here, so that's the first length, 28 there. Then I've got the last length, which is 5, plus 2 times the other bits in the middle, that one and that one, I reckon a 23 and 14. And then that will give us a grand total of 267.5. So therefore, in the last 20 seconds, then the distance is 267.5 plus that 12.5, which is going to give us 280 meters. Which reminds me, actually, I forgot to add that 20 onto this here for the first 20 seconds, I believe. So that adding that 20 onto there, so then in the first 20 seconds, it would have been 290, yeah, 290 meters when you add that together. All right. Now, guys, for the sake of GCSE, okay, I was really taking this apart in case somebody, an A-level student, probably was going to be watching this video. But for the sake of GCSE, literally, because it's an estimate and you're not required to do like all of this nitty-gritty stuff, you don't know the trapezium rule in GCSE, literally just turn that into a massive triangle like that, okay, and then just find the area of that, okay. For the last 20 seconds, I'd probably cheat a little bit, and I would probably go, okay, I've got some sort of a trapezium there, and I'd find the area of that trapezium and then turn that into a triangle at the end and then add the two areas together. Okay, it is an estimate. You're not going to lose marks for it. Okay, the answer isn't going to be exact. If you want an exact answer, you have to integrate. There's no other choice, and that will only concern A-level students. In addition to that, if you're asked to find the acceleration, I think I should probably just do a different kind of graph for that. Let's just say the graph looks like that, and you're asked to find the acceleration. If that's the case, they will pretty much give you a particular point to find the acceleration. So let's just say we're finding the acceleration at point A. You literally need to just draw a tangent at that point. So I'm just going to draw a quick tangent there. You draw a tangent at that point, and then you can use your rise over run on that tangent. So you might just want to do your rise over run like that to find the acceleration. So that's going to be the velocity there, and this is going to be the time here. So in case it's a curve where you don't have constant acceleration, which you don't have here, then you draw a tangent at that point and find the gradient of that tangent. All right. Anyway, guys, overly long video, this one. If you have any comments, please leave it down below. But I hope you learned a little bit today about velocity time graphs. There are more things that you need here for GCSE. So if you're doing A-levels or beginning to do A-levels, then you will find some of these other things useful. All right, guys, have a good one.